Hello everyone. In last lecture we have already discussed about different types of failure criteria which are widely used in the field of fatigue design purpose. In today's lecture I will discuss about another very important fatigue design criteria you can say which have a wide application in the field of fluctuating types of fatigue design. Today which I am going to deliver, that lecture is based on modified Goodman diagram. So, I will discuss in details about first modified Goodman diagram, then I will solve some problem based on this modified Goodman diagram. So, this is the content of today's lecture. First of all, I will discuss about detail on modified Goodman diagram, then I will discuss how to solve problem on modified Goodman diagram, and I will solve one problem on this topic. So, I have already discussed that the component which are subjected to fluctuating types of loading or fluctuating types of stresses are designed by constructing the modified Goodman diagram, that I have already discussed in last lecture. For the purpose of that design, the problem generally classified into two groups. These two groups generally are as follows, you can see, that is in one group it is generally considered the component subjected to fluctuating axial and bending stresses. So, this is one group where the fluctuating stress is either axial or bending types of stresses. And second categories generally is this is the another group where the component is subjected to fluctuating torsional shear stresses. Why these two groups generally is categorized? Because these two group require two different Goodman diagram, or you can say two different modified Goodman diagram. Because for axial and bending purpose, whatever the modified diagram we use, the procedure or steps used there is more or less similar to each other. That means step and other things is similar. Whereas in case of fluctuating types of torsional shear stresses, here the some criteria or you can say some steps we followed which is different than axial or bending types of stresses. This you should keep it in mind. That is why two different categories or two different group generally we make for this what it is called fluctuating types of stresses design purpose. Now, separate diagram are used in these two cases already I have written. In this diagram generally the Goodman line, whatever the Goodman line is there, which is generally modified by combining the fatigue failure with failure by yielding. So, whatever the Goodman diagram is there, that Goodman diagram I have already discussed in details in previous lecture. That diagram here is modified with the help of yield line, that you can say. How it is, everything in details one by one I will discuss. Okay. So, there are details about this modified Goodman diagram for fluctuating axial and bending cases generally is discussed in subsequent slide. Here how to draw this modified Goodman diagram, that I am going to discuss now. So, in this diagram generally first of all we need to draw the axis system which I have already discussed. Here the horizontal axis represent mean stress sigma m. So, here the horizontal axis represents the mean stress axis and the vertical axis represent the amplitude of the stresses. So, if in a fluctuating stresses there is maximum value is sigma max and minimum value is sigma mean, then we know this sigma amplitude is sigma max minus sigma mean by 2, and we also know that mean stress generally sigma max plus sigma mean by 2. We know these things. So, that thing generally for different types of loading cases, generally this is plotted in this coordinate system. Now, first of all we need to draw the modified Goodman diagram. First of all, for drawing modified Goodman diagram, what are the steps we need to follow, that I am going to discuss now. So, first of all, we need to draw the step 1. First of all, we need to draw the Goodman diagram. So, what is Goodman diagram? I have already discussed. So, Goodman diagram I am drawing here in different color. So, we know, let us consider in horizontal axis there will be ultimate strength, and in vertical axis there will be, this I am drawing is endurance strength SE. Let us consider this point R A and this point is B. Now, I am joining these 2 point A and B. So, this AB line is called Goodman diagram. So, here I am writing AB line, Goodman diagram. First of all, we need to draw the Goodman diagram AB. Second step, what we need to do? We need to draw a yield line. So, step 2. Now, draw a yield line. We know this yield line also generally is called first failure line, that I have already discussed in previous lecture itself. So, second step is drawing yield line. So, how to draw yield line? For drawing yield line, generally we have to take both the axis yield stress value, that is I am drawing in abscissa, I am drawing the yield point as y t. Let us consider this point is representing by C. Let us consider, let this is C point. Okay. By considering the same magnitude y t, S y t, that yield stress value, I need to take another point in coordinate. Let us consider this point represent D point, here the magnitude also S y t. So, after that, once we draw a straight line by joining this DC. So, this DC line represent the yield line. So, DC line is actually the yield line. This you should keep it in mind. Okay. So, you can say this is our yield line and this AB line is what it is called Goodman line. You know this thing. Now, this AB and DC. Now, third step, we need to find out the intersection point of this AB and CD line or this crossing line. So, step 3, this will represent what? This will represent the intersection point of what it is called AB and CD lines intersection point. We need to find out. Let us consider this AB and CD's intersection point is, let us consider P. I am considering, let this point is P. So, here one things we need to know, that you see A, P, C, and let us consider this origin of this axis system is O. So, here this, so step 4, we need to define the safe zone and what it is called failure zone. So, here the zone A, P, C, O is called safe zone, which is based on what is called fatigue failure criteria, that is Goodman line, as well as you can say by yield line CD. So, you see this A, P, C, O is called the safe zone, which is called modified Goodman diagram, which is called what? This is called modified Goodman diagram. This you should keep it in mind. So, which zone is called modified Goodman diagram? You can say this zone. So, I am just showing in dotted line. So, whatever the zone I am showing, that is OAPC, or you can say APCO, this zone is called generally modified Goodman diagram. This you should keep it in mind. So, here one thing you should keep it in mind, all the points inside this modified Goodman you can say diagram should cause neither fatigue failure nor yielding. So, here, so in this zone APCO zone, it is neither subjected to fatigue failure nor it subjected to yielding, because it is inside yield stress region, that you can say, as well as according to Goodman diagram it is also in safe zone. That is why it is neither yielding nor what it is called fatigue failure in this zone. So, what we observe, this APCO is called safe zone, which is also called modified Goodman diagram. So, all the point here generally inside this APCO zone, you can say neither fatigue failure is taken place nor yielding is taken place in this zone. So, here I am writing, it is neither fatigue failure or yield failure is taken place, you can say. Okay. This is a step 4. So, here the modified Goodman diagram, which generally combines fatigue criteria as represented by Goodman line, you know, and the yield criteria as represented by, you can say, yield line. So, here you should note that AB is the here you should note that here AP is the portion of Goodman line, you can say AP is the portion of Goodman line, and here you can see PC, and PC is the portion of yield line, you can say yield line. This you should note down. Now, in this diagram, if the mean stress value, mean stress means along horizontal axis, is very large, let it if the mean stress value is very large and your amplitude is, let us consider, is comparatively small, very small. So, in this case some point can lie in the zone of what it is called CPB. Let us consider some points we are getting. Let us consider this P1 point, which is lying in the portion of what it is called PCB. So, this PCB zone, when it will come? When you can say sigma m is comparatively very large and you can say amplitude is very small, this you can say. For this condition you can get some point which is outside this modified Goodman diagram, okay, which is lying in the zone of you can say P, B, C zone. Okay. Now, so in this zone this P point you can observe that is safe based on you can say Goodman line AB. P1 point is safe based on Goodman line you can say AB, because it is lying below the AB line. So, it is safe line according to Goodman line, but once you will see it based on what it is called yield line, this point is not safe. So, according to yield it is failure point, that means yielding already is taken place. So, it is yield on the basis of you can say first line. So, that is why once something is fail according to yielding, then you should keep it in mind, this will result in failure irrespective of safety in fatigue failure. What I am telling, understand? Though it is safe due to Goodman line, but as it is failure by yielding, that is why here of this fatigue related safety will not consider, it is already you can say fail, this you should keep it in mind. So, that is why you should note it down. Once a point lying outside this Goodman you can say modified Goodman diagram, then this will result in failure irrespective of safety in fatigue failure. So, this P1 point is as it is yielding, that is why what happens, it is already failed. So, this portion you can say CPB, this CPB zone is a vulnerable portion you can say. That is why you see the portion PB of Goodman line is a vulnerable portion and need correction. This you should keep it in. Why this modified Goodman diagram is come into picture? Because on the point coming you see outside this PC zone, that means yield line zone, then it will fail. But you can say according to Goodman line it is safe. But what happens, once something is failed due to yielding, then what happens, the safety related to fatigue is not generally considered there. That means it is generally considered as a failure component. This you should keep it in mind. Okay. That is why this P1 point is a point which is you can say is a failure point. That is why generally this modified diagram is coming into picture, because this PB portion of this Goodman line. So, here I am writing this PB portion, PB line of Goodman line you can say is a vulnerable portion, is a vulnerable, is a vulnerable portion which needs correction. Generally this needs correction, which needs generally correction. Due to this thing, this modified Goodman diagram is come into picture. This you should keep it in mind. So, as this PB portion is a vulnerable portion and which generally need correction, this is the reason to modify the Goodman line. This modified Goodman diagram is widely used generally for designing a component, structural component subjected to what it is called fluctuating types of axial stresses, bending stresses, or generally for torsional case this modified Goodman diagram is generally used in separate way. That also I will discuss in subsequent lecture. Okay. Now, for generally design purpose, what we need to do? For design purpose, generally once we go for designing or solving some problem based on this modified Goodman diagram, first and foremost thing what we need to do, we need to draw a load line. So, this load line how it's look like? So, a load line, let us consider I am drawing a load line OE. So, OE is a load line. Here this load line OE which should have a slope, let it makes a angle with horizontal axis is theta. So, this will makes generally a slope of tan theta. What should be tan theta? You can write tan theta can be written as, this is sigma A and this is sigma min. So, tan theta you can write as like this. So, then step 5. So, what is step 5? So, first of all you already by following this step 1 to 4 you need to draw the what it is called modified Goodman diagram. Now, once we go for solving on problem or design on component, then this step 5 onwards we need to follow. First of all we need to draw a load line, you can say OE. This OE which makes an angle theta in horizontal axis such a way, so that tan theta should be equal to, you can say, sigma A by sigma m, that means amplitude by mean stress. Now, this amplitude by mean stress you can write in different way, like what happens, let us force amplitude divided by cross sectional area of this component, then you can say force mean force divided by cross sectional of this component, then what we can write, this we can write as Pa by Pm. So, as well as this also we can write. So, this is in case of, you can say, in case of actually loaded case we can write like this, okay, Pa by Pm. What is Pa and Pa mean? Pa is actually you can write as maximum force minus minimum force divided by 2, and you can say mean force is equal to, you can say, maximum force plus minimum force divided by 2. These are the things you should keep it in mind. This is in case of what it is called bending. In case of bending stress case, what we can write? In case of bending stress case, we can write as tan theta, we can write as, you can say, m bending amplitude, that means bending moment amplitude divided by bending moment mean. How it is coming? Little bit I am explaining, then it will be further more clear to you. We know that according to pure bending, we know bending stress is equal to bending moment into y divided by I. Okay. I is second moment of area or moment of inertia, you can say. M is bending moment, MB is bending moment, y is the distance from neutral axis. You know this thing. So, this is generally called bending stress. Generally y is the outer line, you can say, or outer layer of that structure from neutral axis, and I is the, generally this I is a what is called geometric parameter, it is area moment of inertia, you can say. So, that is why you can say this sigma B is depends on the depends on only, you can say, this bending moment MB, if other parameters are constant. My because is yi and I for a particular structural component, generally it will be constant. That is why what happen, it depends on, you can say, MB value. So, this MB will be maximum, you can say, when you can say your bending moment will be maximum. Okay. So, similarly sigma b will be minimum once bending moment will be, you can say, minimum. So, by this generally once similar way generally we need to find out what is MB amplitude. MB amplitude will be generally, you can say, MB max minus MB mean divided by 2, and similar way actually whatever the way generally we used to calculate, and MB mean also we can calculate. This MB mean also we can calculate as MB, you can say, max plus MB mean divided by 2. So, by this we can calculate the things. So, that is why I have written, in case of bending stress case also we can write tan theta is equal to MB amplitude divided by MB mean. So, here the point, let us consider the point which is crossing this AP line, or you can say modified Goodman diagram at a point x. So, this x point corresponding to, you can say, it will have a mean stress value as well as it will have a amplitude value. You can say let this x point, I am writing this x point have a coordinate SM, and this I am writing S, you can say, amplitude. Okay. So, what is the coordinates of x? Always you should keep it in mind, we should take that point which is cutting the modified Goodman diagram portion, outer line, that point we need to take. Okay. So, that is why it will have a coordinate of SM and S amplitude. So, the point x indicate the dividing line, this you should keep it in mind. So, what is the point x? It indicates the dividing line between the safe region and the region of failure, because below this x you can say point, the portion is safe, the outside of this point x is, you can say, is the failure zone. So, the coordinate of the point x represent the limiting value of the stresses which are used to calculate generally the dimension of the structural component which is subjected to a fatigue stress like SM and SA. What I am telling, understand, this you should keep it in mind. So, this is the limiting value, x represent the limiting value. So, what now for finding out the dimension of the stress, dimension of the component, what we need to find out. So, step 6 is we need to find out the x component, that is your SM and S amplitude, and step 6 this SM and S amplitude generally we will use as a, you can say, limiting value. So, this limiting value is the, you can say, where generally we did not consider factor of safety. By considering that factor of safety, we need to find out what should be the allowable or permissible what is called, you can say, mean stress value and amplitude value of that structural component. So, that is because you see this is the limiting value, just because this is lying on the boundary of that safe zone. Okay. That is why if you consider this thing, it is okay, but what happens here, you are not considering any factor of safety. But for design criteria, generally for fatigue types of loading, we need to consider some factor of safety. Let us consider factor of safety, I am representing is a Fs, which is equal to, let us consider n. So, by this factor of safety, generally in step 7, we need to find out the what it is called allowable amplitude and allowable mean stress value of that component. Based on this allowable mean stress and allowable amplitude stress, we need to find out the dimension of the structural component. This way generally we need to design the component. This is very interesting way to find out the design dimension of a component subjected to axial or you can say bending types of stresses, fluctuating stresses. Okay. So, how to find out these allowable stresses? So, allowable amplitude of the stresses will be generally whatever the limiting value we got from this point x, that is A divided by factor of safety n, and we can find out sigma mean which is allowable. This you should keep it in mind. So, here I am writing these are all allowable or you can say permissible or you can say design. So, mean stress will be Sm divided by factor of safety n, this you should keep it in mind. So, based on these different steps using modified Goodman diagram, we can what? We can design a component and we can find out the dimension of that component. Now, for a given dimension component, you need to find out what should be its maximum permissible, what it is called amplitude of stress, maximum permissible mean stress, that also you can calculate. What I am telling, understand? If in inverse way also you calculate the permissible stress value of that component if the dimension is given. Okay. So, means two different way you can design the component as per your requirement. What I am telling, in one cases you can find the dimension of the component, in another cases let dimension is already given, you can find out what should be the what it is called permissible stresses of that component, that also you can find out. Okay. Now, one problem once we will solve, then it will be very clear to us. That problem now I am going to solve. Okay. So, this is the problem statement you can see. This problem I will solve based on modified Goodman diagram. So, a cantilever spring, here you can see this is a cantilever spring, you know cantilever mean one end fixed, another end free, and at this another end there is a point load P, here you can see. So, a cantilever spring made of 10 millimeter diameter wire is welded at fixed end. So, it is welded here, you can see as shown in figure. Okay. The wire is made of stainless SS, actually stainless steel, which has a ultimate stress sigma ultimate and yield stress is given as 860 megapascal and 690 MPa respectively. Okay. The transverse fluctuating force P. So, this is the transverse fluctuating force P at the free end varies from, so this P varies from plus 75 you see Newton to what plus 150 Newton. So, this is the fluctuating transverse load is subjected to transverse because it is a beam. Beam means here the load is perpendicular to its neutral axis, you can say perpendicular to the what is called its axis, that is generally called beam. Now, the surface finish factor here is given as 0.85, expected reliability is given as 50%, 50% expected reliability if it is, then reliability factor value Kc generally always you should keep it in mind is 1. What I am telling, understand? This stress concentration factor due to welding, there this stress concentration marine factor which is represented as Ke, which is equal to is considered as 0.772. What I am telling, understand? And this load is bending types of load. So, bending types of load case, you know, in case of bending types of load case, your load factor here is equal to 1. Okay. This you should keep it in mind. Here the size factor, as the spring has a diameter of 10 millimeter. Now, according to what it is called marine equation and marine different modifying factor, we know if it is within a range of 0.75 above say 0.75, there generally we can consider this size factor here it is considering based on that equation. Generally it is calculated as K equal to 0.95. So, everything is given. So, a cantilever spring which is made up of 10 millimeter diameter. So, here I am writing what are the things is given. So, solution I am doing. So, first of all diameter of this spring is given as 10 millimeter. Okay. So, in this problem statement itself, so it has given other parameter, ultimate strength is given as 860 MPa, yield strength is given as 690 MPa. Okay. Then load value is given as P, you can say P max is 150 Newton, P min is 75 Newton. Okay.